So chapter 11 is concerned with solutions and colloids. So it's interesting to think about what happens when a substance dissolves. There's a couple of things that has to happen for a substance to dissolve. First of all, the solvent has to separate from itself. The solvent molecules have to rearrange in order to make room for the incoming solute particles, right? Because those solute particles are going to take space. So in order for that to happen, you've got to break solvent-solvent interactions. And that's going to require an input of energy. So it's kind of like, if you've got some visitors coming and you need to sort of, reorganize and get a spare bed for them and stuff, you're going to have to do some work to make room for them. The other thing that has to happen is that the solute particles have to be separated from each other because they're going to be dispersed within the solvent. So you have to break solute-solute interactions. And again, that's going to require an input of energy. So these are the intermolecular forces that we are breaking in each case. The solute then is going to get distributed throughout the solvent, and what will happen then is that the solvent will start interacting with the solute and will form new interactions, new connections, new intermolecular forces between the solute and the solvent that weren't there before. And bond forming processes are exothermic. So depending upon what the sum of the energy changes accompanying these three steps will help us understand what the energy change is for the overall process. So if the strength of the solute-solvent interactions is strong enough to overcome the energy that is used to break the solvent apart from each other and to break the solute apart from each other, then the substance will dissolve. So if I take something like methanol and mix it with water, I'm going to have to break some H bonds in my methanol, and I'm going to have to break some H bonds in my water. But that's okay, because when I form my solution, I will form a whole bunch more new hydrogen bonds, right? So the bonds that I'm breaking are similar to the new bonds that I'm forming, and as a result, methanol has good solubility in water. So this is kind of a general observation. Polar solutes tend to dissolve well in polar solvents because the solute and the solvent can form strong dipole-dipole interactions, which is similar in and these new intermolecular forces are similar in strength to the ones that we are breaking. Now, non-polar solutes don't do well in polar solvents because they're not able to form these strong interactions with the solvent, so they just don't mix well. So if I think about mixing water with something like octane, I'm going to have to break some H bonds in my water in order to form this solution. I'm going to have to break some London forces in my or dispersion forces in my octane in order to separate them from one another. But the types of forces that I would form between my water and my octane would just be the relatively weak London forces. So there's no way that this can work. So when I mix water with octane, it doesn't actually dissolve. I end up with a two-layer system, and the less dense octane floats on top, right? And they just don't kind of separate from one another. And similarly, the water molecules don't separate from one another, and because they're more dense, they sit on the bottom. There'll just be some weak London forces at the layer here, but it's not going to work. So we also talked about this idea when we were talking about not just molecules dissolving into a solvent like water, but also ionic solids, right? So the reason that an ion will leave the crystal and go into the bulk is because it's being tugged on by these water molecules, and if the force of those attractions is bigger than the attractions holding it into the crystal, then it will leave. So putting all of that together gives this kind of general principle of like dissolves like, which really means that polar solutes tend to be more soluble in polar solvents, and non-polar solutes tend to be more soluble in non-polar solvents. And you kind of see that coming up again and again and again in the lab. We talked previously about how dispersion forces can help dissolve O2 in liquid water, and we talked about how important that was for sustaining aquatic life. Now, it's important to realize that dispersion forces are quite weak. If we put some heat into our system and we kind of get our particles moving around a lot, it's easy to break these dispersion forces. So what we observe is that if you raise the temperature of water, you get a radical decrease in the concentration of nonpolar solutes of things like O2. Here's a little graph that kind of shows that. Here's the oxygen solubility. If you look in here, this little region in here, this is what we're sort of, this is, around about what sort of a 4 degrees Celsius rise in temperature looks like for our planet. So, yeah, kind of, I guess maybe like here to about here. And so people are interested in this because that's a fairly, let me just kind of get this right. So yeah, it's about there to about, just in here, I guess, something in there. It's a significant change in oxygen solubility. So what I'm really getting at is people are predicting a several degree change in the temperature of the water on our planet in coming decades, and that results in a fairly large change in oxygen solubility, and people are not certain how marine organisms are going to cope with that. And we are seeing some evidence of what we call fish kills that are resulting from this decreased oxygen solubility. So why does this happen? As the temperature rises, O2 molecules gain sufficient kinetic energy to be able to overcome the weak dispersion forces that keep them in solution. So collectively, interparticle forces are known as van der Waals forces. Non-polar forces that act to reduce solubility in water are often referred to as hydrophobic interactions. Hydrophobic just means water-fearing. Polar forces, they're going to increase solubility in water, and they're often referred to as hydrophilic or water-loving interactions. So when I look at a molecule, I have to consider the overall balance of hydrophobic and hydrophilic interactions in order to kind of predict the solubility of that solute in water. So if I look at something like octanol, I can see that it's got this relatively long non-polar region here, which is going to mean that there will be a lot of dispersion forces between octanol molecules, and they're going to be hydrophobic. They're going to reduce solubility in water. But it does have this bit at the end of the molecule that is capable of H bonding, and that's going to be hydrophilic. That's going to increase solubility in water. So it's got hydrophobic and hydrophilic portions of the molecule. If I look at something like ethanol, I can see here that it does have a hydrophobic region, but it's a small hydrophobic region. And then it has this hydrophilic region, just like we saw in the octanol. So I would predict that ethanol has a much greater solubility in water than octanol, and that is the case. Ethanol can pretty much be dissolved in water to any extent, whereas octanol is very sparingly soluble in water.